Imagine a world where light, the very essence of energy and movement, can behave like a solid. It might sound counterintuitive. Light is supposed to race through the universe at blazing speeds, illuminating everything in its path. But in a remarkable twist, scientists have uncovered a bizarre phenomenon. Under the right quantum circumstances, light can be made to act like a supersolid. To truly appreciate this quantum marvel, it helps to start with the basics. In classical physics, solids are defined by the orderly arrangement of their atoms, each one locked into place in a repeating pattern. Liquids, on the other hand, flow and shift, their particles dancing past each other. And light? Light is energy. It travels as waves, or, on the quantum level, as particles called photons. Yet it doesn't freeze, flow, or form rigid structures, or so it was once believed. But then comes the concept of a supersolid, a state of matter where two seemingly incompatible properties merge: rigidity and frictionless flow. In a supersolid, a material forms a repeating crystalline structure, but at the same time, it can move without any resistance, almost as if it's part solid, part superfluid. This exotic state had been theorized with ordinary matter like helium, but for light? That seemed impossible. Recently, quantum physicists took a bold leap. They engineered conditions in their laboratories that changed the way photons, the fundamental particles of light, behaved. The trick was constructing a quantum playground where light could both interact with matter and with other photons in very precise ways. Typically, photons zoom right through each other without a care. But inside special environments known as optical cavities, filled with ultra-cold atomic gases, interactions between photons can be encouraged, and their movement slowed almost to a crawl. The experiment begins with an optical cavity, a mirrored space that traps photons, bouncing them back and forth a staggering number of times. Inside this cavity, scientists introduced a Bose-Einstein condensate, an ultra-cold gas where atoms collectively behave as a single quantum entity. The photons, forced to repeatedly interact with this quantum state of matter, can start to inherit its properties. Suddenly, the photons act less like individual particles and more like a collective, a single, coherent quantum entity. With careful tuning, the researchers observed something astonishing. The photons inside this system didn't just slow down. They started to arrange themselves in a pattern, forming a repeating structure reminiscent of a crystal lattice. Yet these photons still exhibited traits of a superfluid, flowing through each other effortlessly without losing energy. This was the birth of the photonic supersolid, a state where light both freezes into a solid-like pattern and simultaneously retains the frictionless behavior of a superfluid. Why is this so remarkable? Because it challenges our deepest intuitions about light and matter. The experiment blurs the lines between what is solid and what is energy, opening new pathways for controlling and manipulating light itself. The ramifications ripple outward. New kinds of sensors, advances in quantum computing, or communications systems that harness the extraordinary collective behaviors of supersolid light. And at its most fundamental level, turning light into a supersolid helps us understand the strange world of quantum mechanics, where particles can be waves, energy can be matter, and the universe defies our everyday expectations. We are witnessing the dawn of a new chapter in physics, one where the boundaries between light and matter grow fainter, and our grasp of the cosmos expands in thrilling, unexpected directions. The notion that light can freeze and organize itself as a supersolid is much more than a laboratory curiosity. It's a vivid demonstration of nature's capacity for surprise, a reminder that, even in the realm of the familiar, quantum twists can upend everything we thought we knew. The journey into the quantum world is just beginning, and light, it seems, is only too happy to come along for the ride. Thank you for joining us on this journey into the fascinating world of quantum phenomena. Your curiosity fuels the exploration of new ideas and breakthroughs. By staying engaged and sharing what you've learned, you become part of a community that celebrates discovery and innovation. Remember, every question asked and every insight shared brings us closer to unlocking the universe's greatest mysteries. Keep exploring, stay inspired, And together, let's continue to expand the horizons of knowledge and wonder.